Okay, welcome back. So what I want to do is I want to see if we can't get through the docking procedure, and maybe at the end of this just have a quick look at what some results might look from the docking procedure. Are there any questions before I continue? Okay, please stop me if you do have a question. So first thing I want to do is I want to go into the cluster, and that's fine. So I'm going to log in as usual. Okay. Now I had a folder called receptive. So I'm going to change directory CD into receptors. And then I'm going to just have a list what's in that. So I'm now in the folder, the correct folder. And so now it'd be interesting, for instance, to have a look at 6WNPB. Okay, so let's have a look at, if you want to have a look at a file, you can type less and the file. Now I'm just going to paste it. But please remember that when you type less, the way to exit it is the letter Q. You're going to have to. So here we go. So this is a little bit like looking at it with Notepad++. You can use page up, page down. And if you go down, you can eventually, if you go down far enough, you can see I'm still seeing amino acids. So valine, leucine, etc. are coming through. So you might have to page down quite a lot. You can go right to the end. I don't want to go right to the end with, I think, capital G. I'm just paging down now because I want to get to the end. Oh, there we are. I've gone too far. That's waters. Paging up now. Ah, there we go. There we go. So there we go. So there is a co-crystallized ligand. It's got this, it has this code U5G. So that's interesting. And I can see, of course, its coordinates that are there for U5G. And so I could say, well, hang on, the x coordinate seems between about 5 and 10, so maybe about 7.5. And the y coordinate is maybe about, the middle is maybe about 22. The z coordinate is maybe about 23. That could give me an idea for that. And so we would be able to look at it without doing much, and that would give you the idea that would help you with that. Okay, but the question is, how would you separate it out? But there's this lovely program also. So I press Q to get out of it. There's this lovely program called grep, and I want to see where this code appears in 6WNP. Let's work with the A conformations, for instance. So let's see, does U5G appear in that? And grep says search for U5G in that, and what we'll do is print all lines in that file that have U5G. Okay, so all the co-crystallized ligand, every line, every atom from the co-crystallized ligand has been found and just dumped on the screen. And so we know exactly where that co-crystallized ligand is. Okay. You might not want to dump it all on the screen. You might want to dump it to another file. And so what I could do is do a redirect and send it all to 6WNP underscore A, hang on, I want a capital A, underscore co-crystallize dot PDB. Okay, and so what I've done there now is I have separated it out using the find, the grep command. I've managed to separate out the co-crystallized ligand. Okay, But of course, final thing for those of you who don't want to go through the graphic interface, remember that you can also do prepare receptor. You can't do prepare receptor 4, you've got to do module add. Autodoc MGL tools. Then you can do prepare receptor 4. Every time I press tab on this system, it tells me when it's not got something unique. It warns me, so that's why you're hearing the bell. And so -R, and it's 6WNP _A.pdb. So that's the receptor I want to work with. And I want to do some cleanups. So I'm going to do A, hydrogens. Please, you've got to type this all exactly. And mine is U, waters. I'm just going to do with that. And let's do -E true to make sure it deletes any non-standard. So U5G must be deleted. So the co-crystallized ligand must be deleted. And you see it tells you deleting U5G from that. And so when I look at my PDBQT, if I have a look at less 6WNP, A.PDBQT, which has now been created in one line. If I go right to the end, this is right at the end. This is a very odd. I did a Shift G to get directly to the end. You can see there's no co-crystallized ligand in there. And so this is an apoprotein all ready to go. Okay. So that one line there has done all the work. Has done all the work that we had done before in MGL tools on the graphic user interface. And so this is what I would do in my work, in my day of work, if I've got many receptors to work with. I won't be clicking step by step. I'd rather use a script or something that helps me type this command several times rather than go and tediously work through many structures. Okay. However, I'm going to go back now to working the long way around. I think it's useful. It certainly is very instructive to see what's going on as you work with it. So I'm going back to Autodoc Tools. There's stuff in Autodoc Tools that I just want to make you aware of. Because depending on the username that you have on the system, there may be problems with how Autodoc Tools runs on your system. So I just want to show you some changes that will make it a little bit more robust in terms of how you work. So I'm going to make this larger. The first thing I'm going to do is I'm going to file preferences set and just get it to point to my desktop, this receptors folder in my desktop. Okay, set. So that when I open a receptor, it's in that file. So 6WNPA, that's the one I'm going to work with now. Here it is. So let's open that. Right. Here's interesting. You'll notice that as I open it, there do appear to be hydrogens on it. So my treatment of it, I'm going to be very careful how I add hydrogens. So I really am going to have to make sure that the CHs, the aliphatic hydrogens, are taken away. So I may have to merge non-polar on that. Okay. But first things first, let's edit and delete water. Okay, so so there's no water. And let's go into it and let's see. In here, I see that we do not have any DMS. We've got no non-standard residues. We've only got our co-crystallized ligand, which I'm going to highlight. See if I can see it. No, hang on. There we go. There it is. So there is the co-crystallized ligand, and it's fitting beautifully within the active site of that particular system. So it'd be interesting if we can find other molecules that behave in that same way into that active site. But what I'm going to do for now is I'm just going to select it and save it and write PDB, and this is the co-crystallized ligand. Okay, so I'm just doing exactly what I've done on the terminal, and then I'm going to edit and delete selected atoms, and we have the apoprotein. And so I can file save, and I can write a PDB, PDB, and the name I'm going to just give it is apo. Now my system might complain again, but I'm going to try and proceed. If it complains, then we are going to have to close it and reopen that PDB that I've just saved and deal with it. Okay, so first thing I'm going to do is with the hydrogens, I'm going to just ask it to add all. There we go. So that's fantastic. You'll see some OHs appear. That's really important that we've got those available for hydrogen docking. And edit hydrogens. I'm going to now merge the non-polar. So some original hydrogens that were in the crystal structure are going to be removed, and that's fantastic. Okay. Right, let's calculate charges. Gas go, and then let's go edit atoms and assign autodoc for type. We're done, and then let's just see if we'll be able to save it as a PDBQT, or if it will complain again. It will complain again, so I'm going to restart autodoc tools with my saved apo PDB. Very powerful program, but every now and again there's just some glitches that are causing problems. Right. So file preferences set, and let's go here. Okay. Set and dismiss, and then file read molecule. I'm going to start off with that apo that we've got. See if I can work it again. So edit hydrogens. Get rid of a non-polar first, and edit hydrogens. Add polar only. That will do the same trick. That's another way of achieving the same end. Edit charges, compute gas here, okay, and edit atom types, assign autodoc 4, and will it work this time? Yes, okay. So now we have got the protein PDBQT. Now, unfortunately, I don't have available to me the ligand for redocking. So what I'm going to try and do is I'm going to try a cross-docking experiment. So I need a ligand to dock into 6WNP. So what would be nice with that ligand is to maybe find, so on the ligand, I'm going to open, and I'm going to see, will the 5-REC ligand fit within the active site of 6WNP? So that would be an interesting experiment to do. Of course, it's no use doing this experiment if you haven't validated the docking experiment. So please always validate, try and redock 5-rec ligand to 5-rec to make sure that your docking procedure is okay. But for now, I don't have the ligand available. I've got this ligand. So it'd be interesting to see if I can dock this particular ligand to this particular protein. Okay. And if you have a look, you can see there's a ligand. It's not in any set position, but it's in the workspace ready to be docked to the system. Okay. Right, so we've got a ligand, we've got a protein, so we're all good to go. So we've got to start with the grid. Okay, so what I'd like to do maybe is just to have a look at that co-crystallized ligand. So in the receptors, 6-WMP co-crystallized. Sure, there are a lot of numbers to go through, but I see the lowest number is 5 and the highest number in the X is about 11. So I'm guessing about 7.5, 8 is going to be good for the X coordinate. And the lowest number I see is 20 and the highest is 30, so 25. So 8 and 25. And similarly here, maybe about 24, 23, 23.5. So 8, 7, 8, 25, and 23. Let's see how that works. So let's go here. So on grid, the macromolecule. So we've done the ligand menu, now the grid menu. Macromolecule, it's already open, so I'm going to choose it as being the apoprotein. Okay, it's fine. If it asks you to save, that's fine. Just let it do its thing. We set the map types by choosing the ligand that's already open. There's a ligand. Okay, right. Grid, grid box. Now I need to remember those numbers, and I think it was 8. Hang on. It was 8, 25, and I think 23. So is that looking in the right sort of spot? Let's see. Maybe what I can just quickly do is we can validate it. I'm going to make this bigger because I don't think I've got the active site exactly well. So I'm going to maybe make this a bit larger, but bearing in mind that I would have to rerun the docking to get this to work. And then I'm going to go File, Close, Saving the Current. Okay. So now we've set up the grid. We need to save it, Output, Save GPF, and I'm going to call it 6WNP. 6WNP, and this is a cross-docking. And it's a cross-docking with the ligand from 5-REC. And please put the .gpf on the end. It doesn't automatically do it. Okay. Now what I can do is I can run AutoGrid. And let's run AutoGrid. Please browse. Here we go, and choose it, and then it will come through. And we can set this that it works directly, but I prefer to just browse for it. It's in the scripts research. There we go. And that's AutoGrid. There we go. Please, on some systems, you might have spaces in your name here, in the parameter file name. So please, if there are any spaces here, running this step will not work. So one change that I'd like you to make it more robust, if you've got spaces in your username particularly, is to put a inverted commas at the start and an inverted commas at the end, and just press the enter key to make sure things update, and press and then make sure you out for the second one and also press an enter key. When you press enter, it updates the command line that you see here. And this command line is what is run, what it actually runs. You'll see that it calls the autodoc that you installed, and it runs it on the systems that you have. then you find that it's more robust and the maps will be created fine. AutoGrid runs very rapidly, it's very fast. And you should see at the end of it the map types associated with your ligand. If you want to just double check to confirm that these are working, you can in AutoDoc. You can go to this volume rendering, and let's just open one of those maps and see if it works. So let's look at the hydrogen donor map. Okay, and that seems to be perfectly oriented on the protein. It seems to be nicely, but can we render it? Let's try as an isocontour. Please see the tooltip saying press Shift and mouse click. If you want to add contours, please just Shift click in that window, and you'll add different contours to it. And when you zoom in, if I can make this bigger, I can zoom in. And let's see if I can zoom in there. You will see that there is the cost of a hydrogen donor at that particular point. So you can see where hydrogen donors from your ligand are really wanted in this box, in the search area. Okay, so when you do the docking, it will be able to tell if you've got some hydrogen bond donors, of course, which we do have on this particular ligand. It will obviously want to place them in those positions. Okay. Right, now we're ready for the docking procedure. Let's see if I can just remove that grid. There we go. And so now we are good to go for the docking. So in the docking, we need to just start by setting the macromolecule, which is going to be rigid as 6WMP. For the ligand, we're going to choose the ligand, which is the ligand we got from XTB. And default parameters are fine. In the docking, I like to go through all of these. The search parameters, a genetic algorithm. Yesterday, I made that 100 because I knew I had lots of time overnight to run this. So that's fine. But for now, I just want to go fast, so I'm going to do 10. I wouldn't run it so short I wouldn't do so few runs I wouldn't do so few for my research. I would do a lot more. Okay. And then my docking parameters, I'm just going to accept what they've got. And of course, docking, your output is the Lamarckian genetic algorithm. I'm going to call it 6WNP cross 5reg. And this docking must be a DPF, a docking parameter file. So that when we go and run, and let's go docking, that's saved. So when we go run, we run AutoDoc, we can find that docking parameter file and just please, yeah, let's browse for see program files. This time, please choose AutoDoc for. And what you can do is just check, let's put those in, okay? And make sure there are 2 inverted commas here as well, and press enter. So put the inverted commas in the parameter and press enter, put the inverted here and put enter, so that works. It'll be more robust if you've got spaces in your names. And then we can launch. Okay, so the docking for that particular system is on the go. Okay. So that is another docking that we have on the go. But meanwhile, while that's going on, I wonder if I can open AutoDoc a second time. AutoDoc tools. So there's AutoDoc tools. Let's open it a second time. Leave that one running in the background. Because we ran a docking on the system yesterday, so it'd be interesting to see, can we view the results of this docking that we did. So here's another workspace. And let's go and set the preferences to start off with. Okay. Okay, set. Right. So what I want to do is I want to analyze yesterday's results. So what I'm going to do, analyze dockings and open. And we did the yesterday. I think this is the one I'm after. Okay, and you'll see it's read 100 docked confirmations from 5recdocking.dlg. Use analyze confirmations play to view. So you could go analyze confirmations play. I'll do play rank by energy because it means it'll show you which is the best one and so on. And I'm not seeing anything here because it's off screen at the moment. So I'm zoomed in too much. If I zoom out a little bit, you'll see it there. There it is. And if I go analyze confirmations play rank by energy, then you can see the different confirmations as you go. So that was before it was docked. After it's docked, it's then gone to a different position. Of course, what would be nice is to see it in the context of the macromolecule. So on the Analyze menu, go to macromolecule and open the macromolecule, and there it is. But now it's difficult to see our ligand, so I'm going to highlight the ligand, 5-rec-APA. So there we go, let's highlight the ligand, and there we have it. So there it is, and if we go Analyze confirmations play rank by energy now, there's the lowest energy and so on, and you can see it. Those are the different confirmations that we've got. Okay, and they're all nicely fitting within the active site. My question though is, this was a redocking. We were trying to validate the docking procedure. So the question is, how does this compare to the co-crystallized ligand? How does this molecular docking compare? So I'm going to not highlight it quite so much and just have it like so. Maybe on my protein, I can just create, have it as a surface. There we go. So there, can you see the ligand? Maybe I need a different color for the ligand. Let's just see if I can find a different color. We can do rendering basic. We can maybe change the coloring with a custom color. Okay. No, it's not coming through. Just I've gone blank on how I normally do it, but we can change the color. We'll do that in the next time. But what I want to do is I want to open the co-crystallized ligand, 5-rec-A co-crystallized, and there we have it. Can you see that the docking seems to have found a pocket that has the co-crystallized ligand is not occupying. So that for me is quite interesting. We're trying to validate our docking procedure, and yet the docking has not reproduced the pose that is shown. Now there are two ways to proceed. One is to improve your docking procedure, maybe trying to run the docking many more times so that your docked conformation reproduces more accurately the ligand site. And we could try that. Alternatively, we might proceed knowing that perhaps this ligand has been made more flexible compared to the co-crystallized ligand. We could maybe prevent that. We could maybe remove torsions on that. If there's through conjugation rigidity in the ligand, that might be one of the reasons why it's able to bend in molecular docking procedure and not follow that. Be interesting to see the other conformations. Are any higher energy conformations that more closely mimic the co-crystallized ligand. And I've been through 23, and you can see number 33 is not too bad. It's not perfect by any means. So yes, it does seem to be able to reproduce it in some situations. And so number 33 seemed to be quite good. And my suspicion is that this ligand is not really as flexible as it's being made out to be. So you can see there are confirmations that it is generating that closely match, but of course they're higher in energy because perhaps the software is not taking into account additional energy cost of twisting certain torsion angles on this particular ligand. Are there any questions? Right. If there are any questions, please do email me. But what I will want you to do is at least get molecular docking on at least 2 systems. So by tomorrow, have you been able to redock 2 systems? And then by tomorrow, certainly tomorrow, you certainly want to be able to analyze and say, is the docking good? Is the docking reproducing the crystallized system or is it not? Okay. Right. And tomorrow I want to address a question many of you had, is what if you've got 100 ligands from zinc? And you presume that at least one of those 100 might be better than known compounds that have been tested already against this particular enzyme. How do we pick one of those 100 to test? There are 2 ways to go about it. We'll often, in our lab, we'll often test all 100. We'll go through it, but that might be a lot of work for you to do. So what I want to do is I want to introduce you to some of the physicochemical properties and how we can get those from Open Babel. And that might make you a choice, might give you some information on which to make a choice to choose 1 or 2 of those 100 ligands that you've got from zinc. Okay. Any questions? There are no further questions. I'm going to stop it there. And please feel free to email me. And please feel free to ask for an extra Zoom session where you share your screen and I'll help you troubleshoot through the system. Okay. Any questions? Last questions before I close? Okay. All right. I'll see you then tomorrow, unless you've called for another meeting.